Okay, so yesterday we spoke a little bit about this context, right? That birdsong is learned. There is interest in thinking about sequence production. We talked about neural models, and particularly we looked at the SynFire chain, and using a simple leaky integrate and fire neuron model, we tried to think about what it might mean to set up the SynFire chain architecture. So that's what we did yesterday. I also wanted to just make a quick point. I don't know if I can make it like well enough, but maybe others can add as well. So I think when I spoke to a bunch of you, or you asked me things yesterday, so throughout this workshop, I think you're seeing network architectures of various kinds, right? But it's important to keep in mind that different networks that you pick, maybe the function is different, right? Like why you might see that same motif. So you might see a feed-forward architecture, like you saw it in Anurag's talk with the artificial neural networks. But the purpose then, how the network is trained, how it's treated, may be different, right? So if you just because it's the same computational motif does not mean it's doing the same thing or can be treated the same way. I think multiple people sort of asked questions that indicated this. So I just wanted to say that. And Shakti, did you want to?
So it's true that neural networks have sort of inspired by sort of networks like these. I think it's sort of more helpful to not view from the perspective of does my neural network, knowing the functioning of my neural network, how well does that match the kind of network that she's working with. I think it's not the right way.
Okay, all right. So we also discussed how there are two levels at which modeling can be done in this context, right? So one is you look at neural models and asking what sort of dynamics leads to this kind of timing that we see. The other is to look at the behavior itself, which in this case is song, and ask so there are some stochastic processes that result in song. So can you look at the behavior? So can you look at the song, think of these strings here, and then ask what sort of models, what sorts of probabilistic models could generate these songs. Okay, so this today I think so I'll focus on this bit, and I'll look at one particular model. It's not necessarily the best model for song, and we'll talk about that in the third tutorial. But it's widely applicable to other kinds of sequences as well. So if you're modeling sequences and sequence syntax of any kind, knowing how to infer a hidden Markov model given sequences is, I think, useful. So we'll try and focus on that today. Okay. All right. So the idea is this, that you have, let's stick with the birdsong example. So you have several songs that you get from some lab, let's say, where the songs are being recorded, and then you kind of look at the songs and then reliably identify what the syllables in the song are. You do some sort of pattern recognition. I think you asked about it yesterday. So you do that, and then you turn each song. So I just made all of these up, right? You just turn each song into a set of symbols. Okay, so it's just a string. Each is just a string. And then you ask, given all of these sequences, can I build a model of the syntax, right? So can I think of something like a generative machine? So if I crank up the machine and run it, I should get sequences that are similar to these. Okay. So the first thing that you would do would be what? How would you build a basic probabilistic model? What would you do? So you define states in the probabilistic model. So what is the first thing that you will pick? I mean, what would be a state here? Yeah, the syllable itself, each syllable is a state in the model. Okay.
Sorry, can I ask something?
Yeah, sure.
The question you're posing is you have to get all these sequences with the same architecture or with different architecture?
With one single probabilistic model that accounts for all of these sequences.
So what changes then? When would I get AB? Where would I get AAB?
So these are just different, I mean, well, they're standing in for different songs that a bird sings. So you just see all of the, you look at the entire vocal repertoire of the, well, whatever you manage to record, and then ask what sort of probabilistic model can capture the statistics of these songs. Okay, so yeah, so what's the next thing that you do? You define a state, and then what's the most basic model that you can build? What do you do? So you look at the transitions, so you just count things, right? You ask how many times does A transition to B, how many times does B transition to D, and so on. And the simplest model that you can build is a first order Markov model. Okay, and so the states here are the symbols themselves, right? So each symbol is a state in the model. And so in this representation, so the arrows represent transitions. The number next to the arrow tells you the probability of transitioning between those states in the model. Okay. Yeah. So this just says start state, which just means that, you know, with 67% probability A can start the sequences, and with 33% B can start the sequences.
Accepting DAC, right? But
Yeah, DAC is also.
Okay, good. So you're like one slide ahead, right? So this is a, you can start with this, and then we can ask whether this is a reasonable model or not. Okay, so is this representation okay? Like everybody knows what's in the model, right?
How do you define the
So this just, so the blue states here just say that B has a probability of ending the sequence. C also has a probability of ending the sequence. And the number you can just, you know, given everything else, you know what those probabilities are, right?
frequency.
That's right.
Probabilities are basically the frequency of each song.
Of each transition, right? So DA you count, you know, every time you.
How many times it starts with D is 0.33.
What fraction starts with D?
Is it that, or is it the start state to D transition is 0.33 probability?
Yeah, so the start state is not really associated with a symbol here. So the start state is just something that you have like a dummy state to say, you know, when it transitions, then the song begins or the sequence begins, just that.
What's the range in the length of the strings? Like AB is length 2, DAB is length 2.
So this is just, you know, dummy strings. So in the actual song that we talked about yesterday, if you don't count repeats, depending on what bird you're looking at, it can be like short or long. For the Bengalese finch, you can have up to, you know, 20 syllables in a song without repetitions. If you add repetitions, it's more. Yeah.
So do you feed data first to get this probability from S to A and B? I mean, you have to feed the data first to learn the first letter. Because how do you compute this initial letter from the S state?
Yeah, for a simple Markov model, just from the data you do the counting and then you get the parameters, right? Oh, yeah.
How do you know where the song ends? Is there a pause?
In the actual singing, yeah, there is a pause, and it is much greater than the intersyllable interval and intermotive interval as well. Okay. Anyway, so this is a first order Markov model. Okay. So in general, with Markov models, the idea is that the probability of any particular state only, or the probability of the next state only depends on the current state and not on past states. Okay. So this is called the memoryless property. So the future depends on, you know, like the current state and not the past states. Okay. So that's the first order Markov model, a simple model that you can build, and Ananta and Anish, I think, immediately sort of spotted that if you sort of run this machine, right, so if you take this model and then you create a bunch of sequences from the model, what you will see is, okay, so you can get A, B, you can get D, oh, I think this, the B has come to the next line, okay, so it's actually DAB, okay. You can get AC, but you can also get, you will also get DAC, okay. So just, I mean, this is simple, so maybe you want a better model that, you know, doesn't have this problem of generating spurious sequences. So let's just begin there, okay. So here is another model, okay. What this model is specifically does not really matter. I just want to get one point across. So So one thing that you can do, again remember this is DAB, okay. So one thing that you can do is, the problem is with this state A, right. So perhaps A is actually you have two states for A, okay, instead of just a single state, perhaps both state 1 and state 5 emit the symbol A. So now, does that seem okay? So you have another model where there is now multiple states associated with the same symbol. Okay. So what this would mean, it takes care of this particular problem. Okay. But what this means is that if I give you just these sequences and you see the symbol A or the syllable A, then you don't know whether state 1 generated the symbol A or whether state 5 generated the symbol A. Yeah.
It's not really memoryless. Kind of A, if you're at A, if your previous step is D, then your probability of going through, it changes compared to.
In this case, right. So yeah, so here in the first order Markov model, memoryless. Here there is context dependence. So I was transitioning to the idea that, you know, a first order Markov model need not be sufficient for all sorts of sequences. So in some sequences, actually you may have context dependence and you need models that would capture that kind of context dependence, which is why we are moving on from first order models to other kinds of models. Okay.
We can't represent like repetition of the letters.
Here right now we are not looking at repetitions. There are ways to treat repetitions, but we are not looking at repetitions. Okay, all right. So yeah.
So when you have the level,
Yeah.
then after you with the hidden state.
When you do the what? Sorry.
Level means A, B, and when you do not have the level, just a frequency kind of, then you need the hidden state, right?
I may not have answered what you mean by level.
Level means this is A
Huh.
and this is B. I know that.
Okay.
By seeing that.
Yeah.
But in general, when in input data,
Mm.
we do not have the level of that. So we make this probabilistic hidden state because we do not have the level. So we kind of.
Okay. So you could have. I mean, these are labels for each of the syllables, right? I mean, you have the labels here. There are cases when you may not have it, and then you have to kind of infer what the states are. In this case, you actually do have the labels because it's transcribed song sequences. Okay, so with this second thing, I just wanted to say here is a model where you have this idea of hidden states. Okay, so you would think of these two as hidden states. Yeah.
What are the hidden states here?
1 and 5. They're hidden in the sense that if you just look at these songs, I mean, if you just look at the symbols, you can't tell what the state that emitted the symbol is. So the idea is that you have some sort of process, okay, where there's a Markovian transition between these states, and then there is an emission from each of these states. One of these is not observable and the other is observable. Yeah. So in the case of the simple Markov model, everything is observable, the state equals a syllable. But you could think of other kinds of models where the states are hidden. Okay, all right, okay. So here is an example of a hidden Markov models. Somehow, you know, most textbook examples of hidden Markov models have to do with the weather. Okay, and so here are the states. So cloudy or sunny. And then these are the possibilities, like you can think of these as the emissions or the outputs or the symbols. So it's somebody walking, shopping, and I guess cleaning, and this is some indoor activity and outdoor activities. So you would think of it this way, that, you know, let's say you had somebody's journal, somebody who meticulously kept journal every day and wrote down their activities, and that's all you had with you. You know, you had their journal and you looked, and you know, the person says, I went shopping today, or their world has only these 3 activities, I suppose, and I went walking today, or whatever else, right? I cleaned today, and you just have these entries in this diary. Just given this, could you say what the weather on any particular day where there's a journal entry was, right? So you don't know that. The only thing that you can observe is this person reporting what they did on any particular day. That's what's observable, and then you're trying to infer the process that actually, or you're trying to infer what was it, what were the states, in this case weather, that generated this kind of activity. Okay, so that's one example. Yeah.
I don't get how the weather can be computed. There should be some correlation between the activities for the weather to be computed, right? Like it's like if I'm walking today, that means that it is sunny. Or how does that?
Okay, no, so here, so if look at this, right? So when it's cloudy, you're not very likely to walk, right? You're more likely to, I guess, stay indoors and clean, right? So the probability of it being a cloudy day and then you staying in and cleaning is
That's
high.
the assumption, right?
Yeah.
So if the probability of the probability of cleaning is higher, then you assume for the hidden state you assume it to be cloudy.
When it's a cloudy state, that's what you would expect. So now, given that you see, I cleaned and then I did.
There is an existing repertoire of information, and then there is a journal entry.
You're assuming that there's some model of the world and everything is happening according to that, and you're asking what is this model, right? Okay, so you could have something else like, so here is a sentence. Brownie points for anybody who says where that sentence is from.
1984.
No, okay, no brownie points. Okay, so here is a sentence, and you could ask things like, from here, there could be another layer that you could think of, right, which is parts of speech and transitioning between different parts of speech. So you could like have a whole corpus and then ask this question of, what is this hidden kind of transitions between parts of speech, for example. Okay. And also, I think, Aishwarya, you in your introduction, you said that you work with HMMs. So it might be useful to tell everybody in your context what are the hidden states and what are the output symbols. Yeah.
So I work with modeling sleep using HMM. So in Drosophila, sleep is basically active and inactive states. So the two known states, it's a two-state variable. So transition will be from an active to an inactive state and an inactive to an active state. So when I plug in the probabilities into a HMM model, the hidden states of sleep, which are light sleep and deep sleep. So based on the context information of the inactive to active transitions, so you can imagine that there will be inactive to inactive transition as well and active to active as well. So based on these transitions, you can get light sleep, deep sleep, early wake, and late wake transitions of sleep in a fly model. So I used HMM to.
Okay. So the symbols in your case are actually active or inactive, and you have a sequence of this active, active, inactive, active, something like that. And then the states are light sleep, deep sleep.
Fully wake and early wake.
Yeah. Okay. So and there are 4 states in the model. Okay. All right.
So what the visibility is?
Active or inactive.
Oh, okay, that's the
Yeah.
visibility.
That's visible, and the hidden is the 4 sleep. Okay. All right. So what we are going to do is try and figure out, so the interest is in finding out what these transition probabilities are and so on, right? Like that's what we would like to infer. If you have that, then you have a model that you can use to generate sequences or think about, what might be the underlying process generating the sequences. Okay. So that's what you're going to do, and I would really recommend that you write, because we'll do some Blackboard work and it'll be good to follow along and okay, so what are the parameters of a hidden Markov model? Okay, so these are the things that you should specify if you are specifying a hidden Markov model. One is the number of states in the model, and let's call the set of all possible states S. So there are n of them, and I'm going to use Qt to represent the state at time t. Okay, and then m is the number of distinct observation symbols per state. Okay, so like when it's cloudy, you may do all 3 activities. Okay, just with different probabilities. So the alphabet in that case would be those 3 activities. Okay, so the m is the size of the alphabet. and let's say the output symbols are little v1, v2 and so on up to vm, and at time t, when the state is qt, the observation is ot, okay, and that's the sequence of observed symbols. It's a sequence of length capital T. Then we have a state transition probability distribution. So, let us call that A. What Aij would stand for is that the probability that you transition from state Si to state Sj. So, given that the state is Si, what is the probability that you transition to state Sj? Okay, so that's the transition probability. So, this would be, I mean, in matrix form, this would be an n by n matrix. Yeah. Okay. And then there's also an observation symbol probability distribution. So, think about the activity. So, this is rainy and sunny, and these are the activities, right. All right. So, there's a probability distribution associated with the observation symbol. So, what this means is that little bj k, what it means is that state j, with what probability does it emit k, symbol k. Okay, is that okay so far? Like anything that needs clarification? K is the symbol. So, j is the state and k is the symbol. So, cloudy and cleaning. Okay. And then you also need an initial state distribution. So, to generate a sequence, what could be the first state, right. So, associated with every possible state, you have some probability that it begins the sequence. So, that's pi. Okay, so, in matrix form, so you have a transition, this is a transition matrix. The rows would, I mean, so if you add up these numbers along a row, that would add up to 1, right, probability of transitioning from this state to each of these other states, and if you add it up, that sums to 1. The other, this is a square matrix, this is the emission matrix, transition matrix and emission matrix. You have the states along the rows and the symbols along the columns. Okay, so, it would be an n by m matrix. Okay. Yeah.
The states and observations. So, in reference to the previous example that you gave,
It's a cloudy sunny
Cloudy
example.
sunny.
Yeah. So, this would be, you would have n equals 2, S1 cloudy, S2 sunny.
that's the hidden.
That's the hidden, that's the states. And then you'd have 3 possible symbols. So, walking, shopping, cleaning. So, that's 3 of them. So, K would be, yeah, K represents the symbol and there are m of them. So, is that okay? Okay. Yeah.
So, like in terms of standard random variables, you're saying S1 up to Sn are random variables, time sequence random variables, and the values they can take up is V1 to Vn.
Yeah, so Si can take up the values, well, whatever the first state is, till n of them.
The value is V1 to Vn.
No. So, V1 to Vm are the outputs, right? It's the symbols. So, there are 2 things, right? So, if you go back, these are the states and these are the symbols.
By states,
So,
you mean the hidden states?
Yes.
Symbols are the observable states.
Yeah. If in a hidden model, the states and symbols are not the same. Yeah, Karan, is that okay? Okay. All right. Okay, so so a model would basically have 3 things. It would have the transition matrix, the emission matrix, and the initial state distribution. Once you give that, you know what n and m are, how many states in the model are there in the model, and how many symbols are there, right? So that's just notation to say what the model is. So what we're going to do now is the following. So we're going to talk about what is called the Baum-Welch algorithm. Okay, and it's used to find the parameters of an HMM. Okay, and we look at it in a few different, well, in a sequence of things. So first, so the idea is this. Actually, if I give you a model, if I tell you here is an HMM and here is a bunch of sequences, you can ask this question of, okay, given this model, I look at the sequences and I calculate appropriate proportions of, transitions, etc. And I can ask this question, okay, is this model a good model given the sequences that I have? Okay, and if you see that it is not good enough, however we define good enough, then you want to change the parameters in your model and then check again if your model is good enough or not. Okay, so that's what the Baum-Welch algorithm does. There are few parts to it. So the first part, we will calculate what are called forward and backward variables. Okay, and given what we find here, we'll update the parameters. Okay, and once we do that, we'll ask this question of, what is the probability of the given whatever observation sequence you have given the model. Okay, and you check that and then make a decision about whether you needed to change anything. Yeah.
This is better way.
No. So, well, so then let me come to this. There are three problems that you typically get posed with HMMs. So the first is, if you're given an observation sequence and you're given a model lambda, how do you efficiently compute the probability of the observation given lambda? Okay, so given the model. The second is, if you have an observation sequence and a model, can you come up, or can you choose a corresponding state sequence, okay, which is optimal? And then the third is, how do you adjust the model parameters to maximize the probability of seeing the observation given the model? What you are talking about is the answer to this, the Viterbi algorithm is the answer to this second question. Given an observation sequence, can you come up with a state sequence? And the thing is, we, at least within the time that we have, we won't tackle that second problem. Okay, but if anybody is interested in, what is the most likely state sequence given an observation sequence, what you need to look up is what Akshay just said, the Viterbi algorithm for that second bit there. Okay, all right. Okay, so let's do this bit. So we are first going to calculate what are called forward and backward variables, and then look at how to update the parameters. Okay. Okay, so we'll first look at what's called the forward variable, and that's the probability of seeing the first t observations. Okay, so you have observations t equals 1, t equals 2, and so on, t of them, right? And so what is the probability of seeing the first t observations and then ending up in state Si? Okay, so that's what the forward variable captures. So let's write that down. So alpha t of I is the probability that you see the first t observations, O1, O2, and so on up to OT, and that the tth state is Si given the model. So this is the joint probability of those two, right? Seeing the first t observations and ending up in state Si, at time t. The model, so A, B, and pi.
Okay. How do you initiate this then?
Okay, in practice what you do is you start with random probabilities in the transition matrix, emission matrix, and the state distribution. And the Baum-Welch algorithm, what it does, helps you do is iteratively improve on the probabilities. So you start with random. Okay, all right. So yeah, the backward variable, it will be useful if you try and write out what the backward variable would look like on your own. So this is the probability of seeing the rest of the observations from t plus 1 to the end. If you are in state I at time t. Okay, so the probability of seeing O t plus 1, t plus 2 and so on up to O t, given that you're in state Si and the model. Okay, so these are the forward and the backward variables. Let's try and write them down. So let's try and get an expression for alpha t of I first in terms of A and pi and so on. Okay, so let's take the first one, right? So at the very first time step, let's think about that. So what would alpha 1 of I be? So it's the probability of seeing that first observation and ending up in state I.
Because it's the same.
So remember, there's an initial distribution.
Pi.
So there's pi. So pi I is the probability of being in state I, and then it's also seeing that first observation. So what else do you need? Emission, right? So emission from state I and the first, whatever the first observation is, right, which is OT, O1. Is that okay? You're in state I and you emit observation 1. So how many such values do you calculate at time t equals 1? Or at any time step, how many such values do you calculate? M for monkey, N for
Hidden states.
yeah, the number of states, right? So for every state, you calculate the forward variable, right, at every time step. Okay, all right. So just to kind of, so let's see, what would, can you write down an expression for alpha 2? So at the second time step, what would the forward variable look like? How would you compute it? So at the first time step, you could be in one of these states. So what you have to do is transition from a state, state I at time step 1 to some state j in the second time step, and then emit a symbol, right? And you could have come to any one of the states from any one of the n states from the previous step, right? So what would that be? So you have Aij would be the transition from state I to state j. There are n of these states. The probability of being in that state in the previous time step is alpha t, right? So this would be alpha t of I, Aij, and then when you're in state j, you emit, so I'm writing, sorry, I didn't write it for 2. I wrote the general form, right? So let's think of it for just 2, right? So you have alpha 1 of I, which is the probability of being in state I at time step 1, and then you transition from I to j, and then state j emits the second observation, right? So this is O2. Sum over all of the states, possible states in the previous step. Okay, so you can write the general form now. So what would alpha t plus 1 of j be? So alpha t of I, and then you transition to state j, and then whatever the observation in t plus 1, right? T plus 1. Okay, is that good? Okay, so that's just the forward variable. Okay, can we now think about the backward variable? Yeah, yeah.
You have the initial state distribution
Yeah.
for the states, right?
Of
Not the
states.
observables. But in practice, you have the data for the observables, right?
No, so but we're looking at, so what are we're trying to get at the transition probabilities between the states, right? Aij. So the idea is that you start in some state. Look at the, so you know, the state that you're looking at is the hidden state, and then you transition, and then you have these observations. So you look at the initial probability of being in the state. No. Yeah, actually none of them are directly available to us in the beginning, right? You don't have the transition probabilities. You actually, I mean, in the sense you don't know the true model. You start with random probabilities to begin with for the initial distribution also, and then you improve that with iterations. That's the idea. Okay, all right. So you have the forward variable. Okay, let's compute the backward variable. So it might be again a good exercise to think about how you would compute beta t of I. So that's this, right? We have an expression for the forward variable. What about the backward variable? So remember, it's the probability of seeing the rest of the observations from time t plus 1 to the end if you're in state Si at time t. So you start at the end. Okay, so what would, so for example, let's start with beta t, right? Like at the very end, the last time point there. So if you take beta t of I, how should we think of this? Like what would we pick it to be? The probability of seeing the rest of the observations from that point to the end. So what's observed after that? Nothing, right? Like nothing is observed after, yeah. So after time step t, nothing is observed. So you set beta beta t of I to be 1. Okay, probability of nothing being observed after that, right? So every one of those states, beta t's would be 1. And from here again, it's useful to think about beta t of I. So you could maybe first try and figure out what beta t minus 1 of j, let's say, would be. So that's something to do, and then you can then figure out what the general form is. So maybe take a minute to try and write it down. You're in state I at time t, and then you transition to state j, time t plus 1, and then emit that last symbol, right? Over, this is over all of the states 1 to n. Okay, so that would be just the previous time step. And if you ask what is the general form of this, beta t of I, this is 1 to n aij bj o plus 1 beta t plus 1 of j.
DJ, we're summing it over all times.
Because the
Which one?
in the summation, inside the summation, Aij
Not
to
over
j,
all times, right? You mean
because
all
the subscript
states.
of okay.
It's not all times, it's all states. Okay. So one way to see the computation of these forward and backward variables is to keep track of it in what is called a trellis diagram. Okay, so this is a trellis for the computation of specifically the forward variable. So again, does anyone remember what the forward variable is? So it's the probability of seeing the observations till that point, and of being in the state I at that time point. That's what it is, right? So if you look back at your expression for alpha t, so you transition from here to this state here and then emit the symbol, right? Plus you transition from here to here and then emit the symbol, plus this, and then you emit the symbol, and then so on. Okay, so the trellis can just be used to keep track of what computations are necessary. What about the backward variable? So it's the probability of seeing the rest of the observations, okay, given that you're in a particular state at time t. Okay, and what you should notice is that both in the case of alpha and beta, so this term actually calculates the probability for the rest of the states, right? So this term here, beta t plus 1j. So you're using that in the computation for every time step. Okay, so these are the forward and the backward variables. When you can, I'd encourage you to go back and sort of think about this on your own as well. Given that we have the forward and the backward variables, how do we now use this? So you know what the definitions of the forward and backward variables are. Can you actually tell me, using these, how would you write down what we were looking for, which is the probability of the entire observation sequence given the model? Okay, so let me show you what these are again, and could you tell me how to write down P of O given lambda using alpha and beta? So alpha is the probability of seeing the first t observations and ending up in state Si. So how would you use that to write out?
If we multiply all the alphas, that's the probability of the entire sequence.
Do you need to multiply all of the alphas? Remember, it's the probability of seeing all of the observations till that point. Just the last one, right? So if you just look at alpha t, like t meaning capital T, right? So this is alpha t of I equals 1 to n, and you can also write it with beta, okay? You could use one or the other, right? So we'll also look at the expression for beta. But does this make sense that you can write P of O given lambda using that final alpha? Is this okay? This one? No, why the emission? Because think about what alpha is, right? So you're seeing the t observations. In this case, you're seeing the entire sequence. So alpha gives you the probability of seeing like the first t equals capital T observations and being in a state I. Right, so this sum, it's the likelihood of observing the sequence up to time little t, which in this case is capital T. You sum over the states.
So
there are n possible states, right?
So when you say alpha ti, it's the probability of seeing the ith state.
And the first t observation.
And the first t observation.
Yeah.
So where is the information about the last observation in that summation?
So it includes the tth observation as well, right? Capital Tth observation. It includes that. Okay. Alright, how do you write it in terms of beta? So you can write the same thing in terms of beta also. In terms of the backward variables, how could you write that probability? So I heard, so you are saying something, yeah. Zero, you mean like the first one, okay. So, so you have pi I, beta 1 of I, and then you emit the observation in the first time step. So, bi O1, and this is for all states. Right? So, you use the first variable because it has information about everything after that. Okay, so this was the first of the HMM problems, which is simply if you're given the observation sequence and a model lambda, how do you efficiently compute the probability of the observation given the model? Okay, all right. So from here we can also, using these alpha, using alpha and beta, we can define a few other variables that are useful in the computation. So the first is this gamma t of I. It's the probability of being in state Si at time t, given the observation and the model, observation sequence and the model. So at every time step, you ask what is the probability of being in a particular state. So this was, again somebody said, like, don't you use Bayes rule here? Yeah, so you look at alpha, the product of these two, alpha t of I and beta t of I, would give you what? Like, how would you interpret the product of alpha t of I and beta t of I? That's the joint probability of seeing up to t and then like beyond. Okay, so that would, and then that's the denominator there, right? That's Bayes rule. Okay, all right. And then you could also from here compute the probability of being in state I at time t, and then transitioning to state j at time t plus 1, given the observation sequence. Okay, so you're in state I at time t. You transition from state I to state j, and then you emit the symbol at t plus 1, and then this is the probability of being in that state j and seeing the rest of the sequence. Okay, so one of them is telling you at every time point you want to know what is the probability of being in each of the states. That's what the first thing is telling you. And the second one is telling you, okay, so given that I can see all of these observations, what is the probability at a particular point of transitioning from, making a transition from a state I to a state j? That's what that second variable is telling you. Okay, so gamma, and I guess this is psi, right? Okay, anything that I can clarify here? Are we okay? Broadly, at least, is the idea. Okay, all right. Okay, so here is Baum-Welch finally. Okay, so Baum-Welch is an what's called an expectation maximization algorithm, okay, which is a larger class of algorithms. It is one kind of expectation maximization algorithm for hidden Markov models. So expectation maximization algorithms are maximum likelihood estimation algorithms when you have hidden variables. So Gaussian mixture models, all of these would be examples of expectation maximization algorithms. Okay, and this is specifically for the HMM. Okay, so what do you do? There are two steps in an expectation maximization algorithm. Surprise, an expectation step and a maximization step, right? So the expectation step is just figuring out how likely is it that the system was in a particular hidden state at some time t, and then how likely is it that there was a transition given the observed sequence and the model parameters. So the two variables that we just wrote down, the sum of these variables, okay, over time, there is, you can interpret this as the expected number of, the first one as the expected number of times SI is visited, and or you can think of it also as the expected number of transitions that are made from SI. So the expected number of times a state is visited or the number of times it makes a transition, and this is the expected number of transitions from state Si to Sj. Okay. So, if you have these expected numbers, remember what our goal is, right? Our goal is to go back and update the parameters of the hidden Markov model. So, in the maximization step, what you do is first update the model parameters. So, pi I, which is that initial distribution, given that you have gamma 1 now, and gamma, remember, is the probability of being in a particular state at a time t given the observation sequence. So, you can update the initial distribution given gamma 1, okay, all right. And then you want to update the transition probabilities. So, what you do is you use the proportions, right. This gives you the expected number of transitions from state I to state j, and the expected number of times you expect you see state I is actually this. Okay, this is the expected number of transitions out of state I. This is the expected number of times state I is visited, and so the ratio of these two actually gives you the transition probability, right, that you are in a state and then you transition to j. Okay, so that's how you update the transition probabilities, and the emission probabilities here. So again, you want to be in a particular state and then emit that observation, again divided by the number of times, expected number of times you see the state I. Yeah.
This formula you are getting from the likelihood function, previous one.
Yeah. From.
But here the prior is I think it's right, the likelihood function. If you use the simple Bayesian formula, so the prior I think.
No, but here you're just counting things, right? You're just finding frequencies and then turning them into you know the expected number of times the transition happens, and you're using that to set up what the new transition probabilities are. Okay, so what have we done? We define the forward and backward variables, use the forward and backward variables to get the expected number of transitions from between states given some model that we have in the beginning, right? And then we updated these parameters so that you have a new model now with updated parameters. And then you ask the question, is this model that you have, is it better than what you had previously, using which you calculated all of those parameters? So the cool thing here is that Baum and collaborators actually came up with a proof for this, saying that using the Baum-Welch algorithm, you're guaranteed that the probability, or this is the likelihood, right, of the observation sequence given the model, the new model, will necessarily be greater than or equal to what you had before. So you're guaranteed to improve your model.
So do we do that for every observation sequence?
Okay, so at the moment we're thinking of just like one observation sequence, but there is a way to think about if you have multiple observation sequences, you modify it a little. Yeah, but it's true for, even if you have many observation sequences. Yeah, so you're guaranteed that this will happen. Typically what you do is you keep track of the log likelihood. So the procedure is simply this, that you check this, it is guaranteed to be better than what you had before. Now you have a new model and you go back and do the entire thing again, right? So you calculate forward and backward variables, you update the parameters, look at the log likelihood, and you're guaranteed to see that it gets better or, is just as good. And you do this again and again till your parameters don't change beyond some predefined threshold. So that is the algorithm. So you start with just random model and then you build and you update the parameters for a hidden Markov model. Okay. So just as a quick sketch, this is what you want to figure out. You pick some, I've just used A, but it's true for B as well. So you just pick some initial model. Okay, it has some log likelihood, and then you use Baum-Welch, you optimize, and you optimize A, B, and actually pi as well. Like that's what you do. Okay. So the notation that we've used today is consistent with this tutorial. It's actually a very nice tutorial. So if any of you is interested and has a chance, this is the one to go to. Rabiner tutorial on hidden Markov models and selected applications in speech recognition. Okay, so the notation is the same, and there are many other examples there that you can work through if you'd like. But yeah, that is the Baum-Welch algorithm. So I'll leave you, with that, and just show you, like, next tutorial we'll go back to the syntax. So now you have a sense of what this is and how you can infer these states, like what algorithm you can use to infer these states. I haven't said the full story here. So we'll talk about, when you look at the songs, are there some things that you need to take care of when inferring the model? For example, I said start with a model, right? And in the case of sunny and cloudy and so on, they're meaningful, and so you know the number of states in the model, which means you can start with some n and some m is known, but you can start with some number of states in the model. But when you have data where you don't know how many states there are in the model, Baum-Welch helps you do the updates, but how do you even figure out, and it's a hard problem, right? How do you figure out how many states there are in the model in the first place? And also, other ways of validating models and so on. So next tutorial, maybe we can take that up. Yeah.
So you have said that initially you are using the random model.
Mm-hmm.
So if you use the random model, then from S state, so for every state the probability will be 0.5. There are 2 states, so there will be equal probability.
Oh, so I just meant pick random transition probabilities. For the initial distribution, you could choose them all to be 1 over n. Like that's a good starting point. Yeah. Yeah.
Do you know the time complexity? And there are like other better.
For forward backward, you need n squared and then times t, right? Capital T, which is and I think this is the most widely used. I don't know enough about whether there are better algorithms in terms of time complexity. That I'm not sure. Okay. All right. So I know that that was working through some probabilities, but hopefully you have a picture of how do you infer these the parameters of an HMM given sequences. Okay. All right. So we'll meet on Monday. Yeah. Yeah. Good.